Oh, hey there. In this video, we're going to take a look at the final kind of handful of trigonometric identities um, that we need for our study of simplifying and verifying trig equations and expressions. So, as our essential questions, how can I apply the double and half angle formulas or identities to verify and solve equations? The warm up is just kind of a question that comes from a practice AP pre-calc test. It says that the function g is given uh, by the function g of x equals 7 times sine of 2x. Which of the following is an equivalent form for g of x? So what I need to see is I'm going to go back real quick and show the trig formula sheet. And you can see on here that I know that the sine of 2x, where is it? Right there. The sine of 2x is equal to 2 times sine times cosine of our variable. Now in this case, we have 7 times the sine of 2x. So clearly 7 is not going to be part of that formula. But sine of 2x can be rewritten as, so just this portion can be rewritten as, put multiplication there, 2 times sine of x and cosine of x. And then if I go ahead and multiply my 7 and my 2 together, I will get 14 sine of x times cosine of x. And that is one of the answer options. That's answer A. So A would be the equivalent form of g of x. Okay, I'm going to try and keep it moving in this video because there's a lot of things that we got to get to. So we are going to learn what's called a double angle identity, meaning we are going to learn a formula for cosine of 2x. Now, you will not be asked to derive this, at least not at Roseville. But I want to show you where this comes from. So yesterday we saw, or in the previous lesson, we saw that if we have the sum of two quantities within a cosine function, where the first quantity is considered A and the second quantity is considered B, the cosine of A plus B is, where's that? Right up here. The cosine of A plus B, I'm looking at this line right here, is equal to cosine A times cosine B minus sine of A times sine of B. So I'm going to go ahead and jump back here. Cosine of A, so this is equal to cosine of A times cosine of B, but both of those are x's, minus sine of A, which is x, minus sine of B, which is also x. Oops, there's a multiplication, not a subtraction there. So with our newfound knowledge of this sum formula, I can say that this is equal to cosine squared of x minus sine squared of x. So what I've done is the argument of cosine went from being 2x to essentially being the same as cosine squared minus sine squared. And that is not equal to 1, okay? But one thing I can say is that the cosine of 2x is equal to cosine squared of x minus sine squared of x. And if I go back to the trig formula sheet, you will see on here that that shows up right there. So this line right here is what we just derived using the sum and difference identities, or the addition and subtraction formulas, however you want to call it. We are able to actually derive that formula. Now, there are variations of that where you could start using the fact that sine squared plus cosine squared is equal to 1. There's a couple different variations of it. But the key point here is all of these double angle identities, and it's called a double angle because the original cosine has 2 times an angle in it, thus the double. We are not going to derive it, but those are the double angle formulas for sine, for cosine, and for tangent. So we actually just use the sine 2x formula without really having seen it before. But you can see that all of these angle formulas are on there. Instead of diving into why these come up and why they work, we're just going to kind of show how they could be used to either verify or solve. And in this case, we are asked to verify the equation sine of 3x is equal to sine of x times 3 minus 4 sine squared. So what I see here is I've got sine of 3x, okay? And what I can do with that is I can actually, if we go back up here to I see I have sine of 2x. I'm actually not going to jump right into these because the double angle of this, like 3x is twice the angle 3 halves x, and I don't want to mess with fractions. So what I'm going to do is I'm actually going to take the left side of this equation and rewrite it as sine of x plus 2x, right? X plus 2x is 3x, so that is a sum. And now my hope is that I can verify that the right side is equal to that left side. Well, sine of x plus 2x, again, I'm going to treat this as A and this as B. If I check back on my formula sheet, I can see that the sine of A plus B is right here. That is sine of A times cosine B plus, and then I just switch A and B around. So sine A cosine B plus cosine A sine B. So sine of A, but in this case A is x, multiplied by cosine of B, which is 2x, plus the cosine of our first angle, which is x, and then multiplied by the sine of our second angle B, which is 2x. Okay. Now, that doesn't look like it's maybe, like, now my goal is to show that this is equivalent to the right side up here. I'm trying to show that they are equal. So what I'm going to do is I'm going to go ahead and now I see that I have a double angle formula here and here. So now we are going to use those new double angle formulas that we have seen. So if I go back, I know sine of 2x, just because we saw that one for a brief second. There's only one variation of that we can use, and that is 2 times sine x times cosine x. And then I'm going to bring down the cosine x that was already here. Okay, and then I have sine x times cosine 2x. Now the tricky part about that is cosine of 2x, I have multiple options, right? I could do cosine squared minus sine squared, or the second variation 1 minus 2 sine squared, or the third variation 2 cosine squared minus 1. But if I look at what I'm trying to verify, I'm trying to make it look something like this. There's a 3 minus 4 sine squared x. So to me, that tells me the fact that I see a constant minus 4 sine squared leads me to believe that I'm going to want to use that version of the cosine double angle formula. Again, I don't know if it, like, I'm relatively confident this is going to work, but there's a lot of algebra involved. So I'm going to swap out cosine of 2x for 1 minus 2 sine squared. So here I have the sine x that I already had, and then here's the exchange, and maybe I should be highlighting this. Here I had sine of 2x became this, and over here I have cosine of 2x is going to become the quantity 1 minus 2 sine squared of x. Okay, now, again, all of this is technically only the left side of that equation. I'm trying to get all of this to look like that. So I'm not going to write the equals sine x times 3 minus 4 sine squared because space is a little limited, but let's go ahead and see what I can do here. I see I have sine x and times 1 minus 2 sine squared. So I'm going to go ahead and distribute that. I don't know if that's correct. Actually, I'm not going to do that because what I see here is I have a sine x and a sine x in both of these, and I am trying to verify that it is the same as something that also has just sine x in it. So what I'm going to do is I'm going to factor out the quantity sine x from both this term and that term. And if I do that, what I'll be left with is 1 minus 2 sine squared of x. That's my first term. Plus, if I look at what happens if I remove the sine x from that second term, I have 2 times cosine squared. So what I'm going to do here is 2 times cosine squared of x. And now I am going to bring back the original. I'm going to bring this down just to kind of help me keep track of what I need to turn this into. So I'm trying to verify that this is equal to sine x times 3 minus 4 sine squared of x. Okay, so clearly we have the sine x is the same on both sides. So I'm going to change this into purple because now I can really set my focus on how do I get this thing in parentheses to look like this 3 minus 4 sine squared. You'll notice that there's no cosine squared over here, right? I don't have a cosine squared in there. So I'm going to go ahead and exchange or sub out that cosine squared in this on the left side of the equation. And if I do, I know that cosine squared, trying to talk and write at the same time, 2 sine squared of x plus 2 times cosine itself. Cosine squared is equal to 1 minus sine squared of x. So again, just to keep it consistent with the orange, I am swapping out cosine squared for the equivalent quantity 1 minus sine squared. And then hoping that that is equal to the left side of that equation. Now, if I distribute this 2 through, I will have with sine x out front, again, I'm going to use technology. I have 1 minus 2 sine squared of x plus, and then if I distribute this 2, I have 2 minus 2 sine squared of x. And I'm trying to verify that that is equal to this quantity on the right side. And at this point, I'm going to go ahead and shrink all of this because we are basically done. Because now when I go to combine like terms, I have a 1 plus a 2. So it's going to make 3. Negative 2 sine squared and another negative 2 sine squared. This is going to be negative 4 sine squared of x, which is perfect because that is what I am trying to verify this thing over here is equal to. That is an exact match that I have sine x multiplied by 3 minus 4 sine squared x. So there is my justification that that whole, that this identity is actually correct. And I verified it. Okay. So the key points here was I saw 3x and decided to turn it into x plus 2x. And then I used the sum formula for sine. And then we swapped out both sine 2x and cosine 2x for their corresponding properties or identities. Whew. All right, so there's that first one using the double angle formula. Okay. The power reduction allows us to go from a sine squared down to cosine of simply just 2x. What that will allow us to do is sometimes solving an equation with squared in it can be a little bit trickier. And so sometimes it is convenient to go ahead and break down sine squared into the quantity 1 minus cosine of 2x all over 2. And then you'll see the identities for both cosine squared and tangent squared. To show you where that's at on this trigonometric sheet, those are right down here in the very bottom right hand corner. Those are the power reduction formulas. So if I come back, we take a look and I want to verify that this identity is, or sorry, I want to verify this equation is correct. So I have cosine cubed of 3x is equal to 1/2 times cosine of 3x times 1 plus cosine of 6x. First thing I see is I got this cubed, and that's going to be a problem. And I also see that I have a cosine 3x here. So what I'm going to do is I'm going to go ahead and take that cubed, which is just saying cosine of 3x multiplied by itself 3 times. And I'm going to break this up into cosine squared of 3x. Right, so I have 1 power of cosine on the left and 1 power and 2 powers of cosine on the right. I'm going to go ahead and rearrange this. So I've got this quantity I'm going to put down first. And then I'm going to put the 1/2 times 1 plus cosine of 6x. And again, my reasoning here is I want, now that I already have established that fact is on both sides, now my goal is to go from here and show that that is equal to that. Okay. So I have cosine squared. So I'm going to use that power reduction formula. So we're going to swap this out here. And if I look back at the cosine squared, it is equal to 1 plus cosine of 2x. So I have to double the angle. And all of that is over 2. So 1 plus cosine of 2x. 1 plus cosine of 2x all over 2. But you'll notice the original angle I'm dealing with in the cosine squared is 3x right here. So when I double that angle, 3x will become 6x. And then I'm just going to bring everything else down. Cosine of 3x multiplied by that is equal to cosine of 3x times 1/2 of 1 plus cosine 6x. And just a reminder, my goal here, because I already have the cosine 3x on both sides, is to verify that this quantity is equal to that quantity. And if you take 10 seconds and look at both of those, they are identical, except this, the 1/2 is factored out. And on the left side, the 1/2 is like part of the fraction. So all I'm going to do here, and I'm going to keep this highlighted to show what I took from the formula sheet, the identity that I used. All I'm going to do to verify this is I'm going to go ahead and take this 1/2 and distribute it. Again, you don't even, technically I'm not even going to distribute it. 1/2 multiplied both of the terms 1 and cosine of 6x. I can just put it over 2 like it is over here. So this is where you have some flexibility of like, how do you want to write the final product? I'm going to keep the left side the same because I kind of like the 1 plus cosine of 6x over 2. And that is equal to cosine of 3x. And again, essentially what's happening is this 2 is going to become my denominator for this entire quantity. So I have 1 plus cosine of 6x all divided by 2. And now I see that I have verified both sides of that equation. So we did eventually use the power reduction formula, but first what we had to do was take cosine cubed and split it up into a single cosine and then a cosine squared. So that is the power reduction. And then finally, the last formulas that we're going to learn about and use are what are called the half angle formulas. Half angle formulas are, hey, if you have sine of x over 2, that is equal to plus or minus, we have to have that plus or minus in there, the square root of 1 minus cosine x over 2. And then you see the other variations for cosine and tangent. Okay, there are all three. And again, on the trig formula sheet, those can be found right next to the double angle formulas and right above the power reduction. Okay. So there are those formulas. Let's go ahead and try and use one of them. And this is a little bit more meaningful, is find the exact value of sine of 67.5 degrees. Now, in the previous lesson when we did the sum of a plus b, we were able to find the sine of 75 degrees because 75 degrees is the sum of 30 degrees and 45 degrees, both of which are on the unit circle. 67.5 is not on the unit circle. There are no decimals on the unit circle. But 67.5 doubled is 135, and 135 is a degree on the unit circle. It is the same as 3 pi over 4. So what I'm going to do now is I'm going to say I'm trying to find the sine of 135 over 2, because the sine of 135 over 2, well, half of 135 is 67.5. So now this effectively is going to be treated as my x from the formula. Okay, and if I go to the formula sheet and look at sine of x over 2, it is plus or minus plus or minus the square root of 1 minus cosine x all over 2. Plus or minus the square root of 1 minus cosine x all over 2. Now, technically the formula does need a plus or minus, okay? But if you think about the location of 67.5 degrees, 67.5 degrees is in quadrant 1, somewhere like right there maybe. Oh gosh, that's terrible. Somewhere up there. Because it is in quadrant 1, we know the sign must be positive, which means I can technically get rid of the plus or minus, and I will just use the positive version. Now I have to be careful with this because actually I will still be able to get rid of the plus or minus, but I'm going to wait on this for just a second. Okay. But no, sorry, getting ahead of myself. 67.5 degrees is in quadrant 1. The sine of 67.5 must be positive because all three primary trig functions, sine, cosine, and tangent, are positive in quadrant 1, which means I can effectively get rid of the plus or minus and just consider the positive version of 1 minus cosine of x over 2. But in this case, x is 135 degrees. So now I just need to know the cosine of 135, or 3 pi over 4. And that is equal to root 2 over 2. So this is a little goofy because I have a square root inside a square root, and it's a fraction that's part of a fraction, which looks terrible to start. So what I'm going to do is I'm going to go ahead and get that positive 1 to have a common denominator. I'm going to do that by calling it 2 over 2, because 2 over 2 is the same as 1. So now my fraction becomes this, which is just a series of 2's. Now I'm going to go one line down, and I'm going to write this as a single fraction over 2, and all of that is being divided by 2. And maybe you've picked up on the pattern by now, but division by 2 and then immediately by dividing by 2 again is just the same as dividing by 4. So this is really equal to the square root of 2 minus root 2 over 4. And you might be saying to yourself, my gosh, we have to be done. What else can we do with that? But when you square root a fraction, some textbooks, some teachers, some courses might be okay with you stopping right there. Technically, square rooting a fraction, this square root, all it's really doing is it is square rooting the numerator and then separately square rooting the denominator. Like that's how we square root fractions, is we just square root the numerator, square root the denominator. And that might not look super helpful, but we know the square root of 4 is actually just equal to the integer 2. So my final step here is I'm going to write this as the square root of 2 minus root 2. So I have what's called a nested square root, a square root within a square root. And then I also have a denominator of 2. And if I'm going to write it like this, I need to make sure that this square root symbol right here does not extend into the denominator, because the denominator is no longer a square root. It is equal to just the integer positive 2. So that is the exact value of 67.5. Now, if you go up to someone and say, hey, I know the sign of 67.5, it is root 2 minus root 2 all over 2. That doesn't help, but it is an exact formula and one way that these half angle formulas can be used. So, again, we have the half angle, we have the double angle, and the power reduction. So kind of 3 sets in one. So just a quick reminder, because we're going to try to use a couple of these to solve some equations. If I see something like this, such as sine squared minus sine minus 2 equals 0, I am effectively treating this as, I need to factor it because I have sine squared and sine to the first. So I'm going to kind of think of it as x squared minus x minus 2, where my x is actually the sine of x. Well, I know this can be factored into x minus 2 times x plus 1. So then I know that this can actually be factored into sine of x minus 2 times sine of x plus 1 equals 0. Again, just treating this single variable here as sine of x over here. And now if I go to try and solve this in factored form, I have sine of x minus 2 is equal to 0, which means sine of x would have to equal 2. But we know that sine oscillates as a wave between -1 and 1. So this portion does not have any solutions. And over here, I want sine of x plus 1 to equal 0, which would mean sine of x would have to equal -1. The sine of what angle equals -1, that happens at 3 pi over 2 in between quadrants 3 and 4. You could also write it as negative pi over 2. And any angle that is coterminal to 3 pi over 2 would also be true here. So that's why I'm going to say plus or minus 2 pi times k, where k is any integer, either positive or negative. So here I've got x is equal to 3 pi over 2 plus or minus 2 pi k. And if you're in my class, we've talked about if we're considering k to be either positive or negative, you technically don't need the plus or minus. You could just say plus 2 pi k. So there's some flexibility in that. So how does that help? Well, let's try to solve something that looks like sine of 2x minus cosine x equals 0. Now, that's a problem. That is not sine squared. If it was sine squared, that'd be easier because I could turn it into cosine squared, or I could turn it into 1 minus cosine squared. And then I'd have cosine squared and cosine in the same formula. But sine of 2x, I need to change using the double angle formula, 2 times sine x times cosine x. So again, from the formula sheet, sine of 2x is equivalent to that quantity minus cosine x equals 0. Well, if I look at my two terms in my equation, this term here and that term there, they do have something in common, and that is they both have a cosine. So I'm going to factor out the cosine x, and that would leave me with 2 sine x minus 1 is equal to 0. Now that's factored, I can say, all right, where is cosine of x equal to 0? And that is equal to 0 at pi over 2. Yeah, pi over 2, and also at 3 pi over 2. So it's true both on the vertical y-axis and the negative y-axis if you're looking at the unit circle. So instead of writing pi over 2 plus 2 pi k, I'm just going to say pi over 2 plus pi k. So that is my solution set. again, or the other way to write this is you could say pi over 2. One other way you could write this is to put 2 pi k and then also list 3 pi over 2 plus 2 pi k. And then over here, if I want 2 times sine of x minus 1 to equal 0, that would have to mean that sine of x is equal to 1/2 if I add 1 and divide by 2 to both sides. And sine is equal to 1/2 at pi over 6 and 5 pi over 6. Those are not symmetric from each other. They're not symmetric about the origin. They're not an equal distance away from each other in both directions around the unit circle. So I do have to list both solutions individually. So I do say this is equal to pi over 6 plus 2 pi k, as well as 5 pi over 6 plus 2 pi k. So that is one way we could use the double angle formula to solve an equation that contains sine of 2x. And finally, if we can make it through before my computer dies, we're going to try and solve this. I see x over 2 here, which to me means I'm going to need to figure out a way to change that. That's a pretty dead giveaway for the half angle identity. So if I go back here, sine of x over 2 is plus or minus the square root. The good news is, guess what? I'm dealing with sine squared of x over 2, which means if I square this quantity, I just don't have the square root there anymore. So a variation of this would also be that sine squared of x over 2 is simply equal to 1 minus cosine of x over 2, or 1/2 times 1 minus cosine of x. So let's go ahead and jump back here. We're going to cash in on that. So sine squared of x is equal to 2 times, and then here's where we're going to swap out this for 1 minus cosine of x over 2. So this is the formula sheet identity that we're using to change it out. But conveniently, I see I have a factor of 2 on both the numerator and denominator. So now my equation has become sine squared of x is equal to 1 minus cosine of x. That's a problem because I have not only one quantity being squared in sine, but I also have the other trig function cosine squared. So in a situation like this where you have sine squared and cosine not squared, I need to go ahead and make the change and rewrite sine squared as 1 minus cosine squared. And the reason I'm going to do that is because now I can gather all the terms on one side and I can go ahead and factor this. So typically I like to move everything to the left. So I'm going to subtract 1 from both sides. Super convenient. That cancels. I'm also going to add cosine x to both sides. That cannot be combined with the cosine squared. So what I'll end up with is these ones will cancel or make 0. And I have negative cosine squared of x plus cosine x equals 0. I personally do not like factoring when my squared term is negative. So I'm going to distribute a -1 through this entire equation. So I'm just going to change everything to the opposite, which is fine because the opposite is 0 is still 0. Now these two terms, cosine squared and negative cosine, do have a common denominator of cosine. So if I take a cosine of x out from both terms, what I'd be left with is cosine of x minus 1. And now that's in factored form, my question is, all right, where is cosine x equal to 0? And where is cosine x minus 1 equal to 0? Which is really asking, where is cosine x equal to positive 1? Cosine is only equal to positive 1 at 0 and then at 2 pi and so on. So I'm just going to say 0 plus or minus 2 pi k. Again, you could just put plus or minus 2 pi k. That 0 doesn't really effectively do much, but I like to put it there just to show the angle that we're coming from. And then where's cosine 0? We already saw that. That is actually equal to 0 at pi over 2 and 3 pi over 2 and 5 pi over 2. So I'm just going to put plus or minus pi times k. So that is the solution set for the equation sine squared x is equal to 2 sine squared of x over 2. So not only did we use the half angle formula, we also swapped out sine squared for 1 minus cosine squared. Hopefully this makes a little bit of sense, but you really do need to just get in there and try it on your own. Thanks for watching.